go from current slide here and also current slide here. Okay. Now, before we get started tonight, there are a few issues I want to make sure everybody understands. Okay? We're going to finish chapter 17, which is just a couple of more problems. Maybe just, well, I didn't make a mark. I always make marks, and I didn't make a mark this time. Okay, at the end of the class, let me give you a couple of your tests back, because I can't give them all back because there's still people with some of them out. So, but even the ones I do give you, there are some people that are not here or haven't been here much, so I've given those back. But if they see your paper, they may see the corrected answers. They get a better score. It cheapens your grade. Don't want that to happen, so just don't be sharing it. Okay, so what we're going to do, finish chapter 17 tonight. We just got a couple more examples to do, and we're through with it. And I gave that test out last time, so hopefully all of you have it. If not, please get it before you go. And then we'll start on chapter, what is the next one? 18, I believe it is. And we'll get as far as we can there. And if we get far enough, I'll give you a test on that one too. It'll be very short, very sweet, hopefully, and that'll be your last test. If we don't get far enough for that to make any sense, then your one I gave you last time will be the last test. Okay? But we'll get as much covered as we can, because I want you to be exposed to as much of the information they say you need as possible. Okay. All right. Okay, let's do the rest of it. Have any of you done the student course evaluations? You know what that is? How to do it? Okay. You said you knew how to do it, right? You know what it is, right? How do you go about doing it? Okay. Right. So what I understand you to be saying, my hearing's not good. An email was sent to everybody, right? About student course evaluations? Okay. If you go to that email, there's a link there. Click the link. You go straight there. It has directions on what your user ID is, what your password is. All that's right there, ready for you. Now, when I said something about email, I got sort of some blank looks. Do all of you know how to access your email, Lawson State email?
I have tried repeatedly and had difficulty in messages.
Right.
I have not had help here.
Okay.
Asking help.
Okay.
Yeah, mine is linked to my Gmail account.
Okay. Yours is linked to your Gmail account. Did you do that somehow, or did they do it somehow?
I did it.
You did it. Okay.
I forgot my password, and I was like, I'm just link everything.
Okay. And I forgot. I haven't called roll yet. Let me call roll, and here I am recording. Okay. And today is the 5th. Yep. Oh. 5th of December, and happy December, everybody. Okay, Jennifer Addison is here. Ashley is here. Tyler's not here yet. Cora's not here. Amber withdrew. Kobe was here but left. Megan is here. You get across to make sure I put you on the right line. There you are. Okay. Nicole's not here yet. Jennifer Stevenson's here. Quinn is here. Shannon's here. And Caitlin's not here yet. All right. 1, 2, 3, 4, 5, 6. 2, 5, and 1, 6. Okay, got it. All right. Sorry, I forgot to mark the roll earlier. So, please, okay. If you don't know, if you can't access it through your email account, then here's the way to do it. It's a little longer, but it's still not too bad. Y'all know computers pretty well. Go to the Lawson State webpage. On the Lawson State webpage, across the top, there's a series of blue tabs, I believe they are. Except one near this end is a bright gold tab. It's bigger than the other, and it says Quick Links. Okay? Any of you ever use that? Quick Links? Okay. Look for that one. Click on that. Now you get a huge menu. You have to scroll and scroll and scroll. Look for something that's anything that would relate to surveys. I think surveys is the key word there. But student course evaluations, surveys, student surveys, look for that. I believe it's something under the S's. And when you find that, click on that, and that takes you to the same place. The email is really easy. Just go to the email, open it, and click on the link, and you're there. This one you have to go to the website, Quick Links, find that topic, I think it's student surveys, and then go to there. Now, about how to get help with that, check with Miss Shannon's her first name. I can't think of her last name. She works in the office here. She's not here tonight. But check with her sometime, and she probably can tell you someone to contact. If you're over on the Bessemer campus, I'd know exactly who to tell you to go to. On this campus, I don't know who the best person is. But, you know, I think she'll be very helpful. She usually is. Okay. If there's any difficulties, I probably would get stuck somewhere there too, but she would probably know. All right. And this is Cora, right? Okay. And the ones who have come in just a little bit later, at the end of class tonight, come by and I'll give you at least the first two tests back. The third, fourth, and fifth test, I've got so many out, I hate to release the correct information on those. The first two, there's still a couple out, but those people haven't been here very much, so, but still don't let anyone see them because that will give them the correct answers and cheapen your grade, so don't do that. All right. Now, I forgot to make a mark. I usually do, and I think I was talking with students at the end of the class, and I forgot to make it. We're somewhere on page 480 or 481, either example 4 or example 5. I don't recall which. I think it's example 4, but let me know. Which, is that where you remember this to be?
Yes.
Which, example 4?
Example 4.
Okay, good. That's what I thought. I didn't remember doing that problem. Okay, and example 4 does not have a slide, so I'm going to have to draw it myself, so I'm going to go to this and go from current slide. All right, and let's talk about the rest of it too. We mentioned this before some of you came in. We're going to finish chapter 17, which is only 4 and 5, and maybe one more slide, and that's all for tonight. I mean, that's all for chapter 17. That's why I already gave you your test, because most of you are already working on that. Okay. Then we'll go to chapter 18, which is, get the correct title, magnetism. Okay. Now, y'all are doing sonography, not, EMR or some of the other things, so I don't see that magnetism is all that important for you. But that's in the course description, so we're going to talk about it. Okay, and if we get far enough along with that tonight, I'll give you your test. I'll tell you which questions will be required and which ones will be optional, and that will be your last test. If we don't get far enough for it to make sense, then this last test that you have on electricity will be your final test. So it'll either be 4 or 5 tests. All right. And then next Wednesday, I'll be back here from 4:30 to 6:30. And anytime you want to come in and bring your test, that'll be fine. Now, none of you are graduating this term, right? Okay. Because people graduating this term, their grades are due in by noon on Tuesday, so that wouldn't work. Y'all would have to get me the test sooner. Now, if you want to get me the thing sooner, if Wednesday's not a good time for you next Wednesday, I'll be on the Bessemer campus. I'm usually over here on Friday mornings, okay, on the West campus. But since the fire in the B building, it's still closed as far as the student told me yesterday. So I don't have an office anymore. I mean, the office is there, but there are not a lot of people in the building. So I'll be on the Bessemer campus on Friday. So I'm on Bessemer campus, all my office hours, which are on my syllabus, and the locator card, except for Friday. I'm now on the Bessemer campus, not the Birmingham West campus. So I'm over there. You can bring it anytime. If I'm not in the office, you can slide it under my door in A building 265. And just ask anybody. Most of the people, regular people there, will know where my office is. It's a strange building, and the numbering makes no sense, and you might have to ask for guidance, but someone will get you to my office. Okay. And I'll be there most of the time, except when I'm giving finals and stuff. All right. Any questions? Okay. Please do the student course evaluations. Okay. All right. Example 4 on page 480, chapter 17, basic electricity. Find the equivalent resistance in the circuit shown in figure 1754. Okay? And that's why I have this up. So here we have, here we have a battery or a power supply. That's probably not a battery, even though it uses a symbol for a battery. They're calling it E is equal to 120 volts. And they put a line over the E, the 0, indicating that is a significant digit. Okay? It goes up and then branches into a parallel circuit that goes to resistor 1, resistor 2, and resistor 3. Okay? Resistor 1 is 7.00 ohms. Resistor 2 is 35.0 ohms. And resistor 3 is 25.0 ohms. All right. Then it branches down here to another parallel circuit, which has 2 resistors in it. I can't draw, but something like that. This is resistor 4 at 20.0 ohms, and resistor 5 at 62.0 ohms. Okay, and then finally that comes back into the low side of the battery. So we have complete circuit here. Okay, find the equivalent resistance of this circuit. So in other words, what does the battery feel like is over here? Okay, all these things are over here, but what does the battery sense? It senses there's one big resistor out there, and I say big, it's a combined resistor. It may be smaller or bigger than, it will be smaller than some of these and perhaps bigger than others, okay? But what do we do? So what would be your approach? Anybody? Okay, this is a parallel circuit, so find the equivalent resistor of this one. So we'll call it REQ. What do you want to call that? I think they call it 6. They just call it R6, so I'll call it REQ6, the equivalent resistor of those 3. And that would be 1 over that will be the sum of those reciprocals. 1 over 7, and for the purpose of your adding, you don't need to put all the point zeros, plus 1 over 35, plus 1 over 25, if I can read my writing. Okay? Those are all in ohms, so you see what the equivalent resistance of that parallel circuit is. Hint, it will be more or less or in between the biggest, smallest, or of these. What would you say? The equivalent resistance is always of a parallel circuit less than the least. So it's going to be less than 7. Maybe not a lot less than 7, but somewhat less than 7.
4.73.
Second?
I got 4.73.
That sounds reasonable. I was going to guess around 5. So R, the equivalent resistance, and we'll call that number 6, is 4.7 what? 73 ohms. Okay? Well, we do the same thing down here. Okay? And here we have, we'll call this REQ, we'll call it 7, because that's what the book calls it. They don't put the EQ, but I like to do that. And that would be, okay, oops, I'll find you. Is it Nicole? Yeah. All right. Now, if at the end of the class, if you'll come see me, anyone who came in that didn't get your first 2 tests, I've got those. I'll give them back to you. I've had them all term, but there's a few people still haven't turned them in, but most of them aren't coming, so I'll return those 2. Now, the rest of them, I have more of them out, so I just don't feel comfortable giving those back with so many still out. So I'll give you those when you come turn in your final. Okay. All right, so how do we find our EQ7? 1 over 20 plus 1 over 62. Now this we know is just going to be something less than 20, okay? Probably not a whole lot less than 20, but something less than 20. What do you get? 15.1. Okay, and that's ohms. All right. Now here we have, you may not think of it as a dilemma, but it is a little bit of a dilemma because we're adding significant digits, but they don't have the same ending to them. You know, this is to the nearest hundredth and that's to the nearest tenth. When we do that, we can't get any more precision than the nearest tenth. So you add these together and you get basically, why am I saying we're going to add them together?
Well, because you're trying to, because the problem says.
Okay, because these 2 are in series with each other. These 3 were parallel, those 2 are parallel, but these 2 equivalent ones are in series because the same circuit goes through both of them. And in series resistances, you add the resistance, not the reciprocals of the resistance. So that way, and that's why, I'm sorry, I jumped the gun. I should have asked the question first. So that would be 14.7 basically plus 4.7 plus 15.1 would be 19.8 ohms. That's the equivalent resistance. Okay? And like I said, it's more than the 7, okay, because you're adding some equivalent resistance, but it's actually less than all the other resistors. Not much less than 20, but a little bit less. So 19.8. And what did they get? They said 19.83, but then dropped it back to 19.8 because you can't get more precision out of the problem than you put into the problem. So that 3 is sort of lost in the sauce there. Does that make sense? Any questions on it? Okay. All right, let's move to example 5, which I think is the last example. And that is, thank goodness I didn't erase my screen, find the total current in example 4. How do we do that? And this, I guess they're probably going to call the equivalent resistance 8, which is of the whole circuit. As I said, this is all the battery sees or feels, is it's having to supply enough current for that. So what would be the current for this? Once you found the equivalent resistance, that's a pretty easy process. What do you do? I is equal to E over R. And that will be this last resistance, the equivalent resistance 8. So that will be 120 volts, 3 significant digits, divided by 19.8. That's already 3 significant digits. Ohms, and what do you get? Something pretty close to 6.
6.06.
Okay, 6.06. Yeah, okay, 6 amps. I couldn't hear what you said at the end. Okay, 6.06 amps, and that's exactly what they got. Good for them. Does that make sense? See how you do it. Once you get the equivalent resistance of a circuit, then you can just use Ohm's law directly. Okay. Now, any questions? Okay. Let me end this. Okay. And move to this. This is the last. Okay. This is the last slide in the text. We already did this one. So the last slide is sort of a summary table you'll find at the top of page 482. Okay? Just a general summary table for characteristics of both series and parallel circuits. Okay? Remember, a series circuit is where the same current flows through every device. So the same current, that means the current through device 1 is I1, I2, I3. They're all the same because it's the same current making its way all the way around. In a series circuit, if the resistances are in series, you just add them. It's just like having one big resistor that's the sum of all those others. Now, what happens with the voltages? Your battery or your power supply supplies a certain voltage here, and then that voltage is dropped as you go through each of those resistors. Okay? And the drop would be V is equal to I times R. So you know the I is the same on all of them. I times R1 would be a drop across V1. I times R2 would be a drop across V2. Drop across R2, that would be the voltage drop across R2. I times R3 would be the voltage drop across R3, and so on. So that's how you get, and all those, when you add up all those voltage drops, that has to equal the voltage supply. Yes?
Okay. What chapter is this? Is this 5?
Okay. That is the chapter we're on now.
17.
Yeah, this is the electricity chapter. It's 7, where did we start in it? 17.3 and went through the one we're on right now.
17.
Through 17 point, is that, yeah, 9. We're not doing electrical instruments. Okay, so that's your series circuit. Your parallel circuits, now this is different. You have the battery or the voltage supply providing the voltage, okay? And then it goes out and the current splits and goes through each resistors. So each resistor has its own current, so the total current is the sum of all the currents. Unlike the series where it's the same current through them all. Now your resistance, like we've just been doing, are added in a reciprocal sense. So 1 over the equivalent resistance is equal to 1 over R1 plus 1 over R2 plus however many we have there. And you have to use your reciprocal keys to do those calculations. But the voltage drop across any of those, if it's one parallel circuit, is the same across every resistor. So the voltage supplied by the battery is the same as the voltage drop across each resistor. So once you know if you know the resistance and the voltage, then you can calculate the currents. Pretty straightforward. Okay. Any questions? All right. And that's as far as we go in chapter 17. So any questions on 17? There's some additional problems. Odd numbers 1 through, 25. Okay. You don't have to do them all, but the odds have answers in the back, and if that would help you working on some of the test questions, by all means, take advantage. Okay. There's other good stuff in the chapter. I don't think it's anything that you will be needing in your work. And I was supposed to meet last Friday with one of the women who teaches the something in the sonography program and the science of it and stuff, and she wanted to get with me on what we were doing in here and to see how we could link them together, so we'll do that. At the end of Chapter 17, there are some review questions. Some of these will be in sections we didn't cover, like 1 and 2, and those at the end after 9. But the rest of them will probably be useful for you to look at. The review problems, and again, I think the review problems, all the answers are in the back of the book. Is that not correct? Okay. So any of those that pertain to what we did, those would be maybe beneficial for you to look at as well. So now we move to Chapter 18, which is magnetism. Okay? So I'm going to end this one and shift this around a little bit. There we go. And pull up Chapter 18, magnetism. This room is cold. Okay. And I went down the hall and it was even colder. So I think there must be low heat in the building today. I don't know why. All right. Chapter 18 is talking about magnetism, which really is very closely related to electricity. Not the same thing, but they're intricately linked to each other. Okay? We're just going to talk about some of the key features of magnetism. We'll get as far as we can, and when we are at the end, we are done. Okay? So, let's take a look at some of the key elements of magnetism. Okay? The first slide here doesn't show up for a few pages. So let me go over the first couple of pages just with what we got. Now, humankind has known about magnetism for probably millennia. Okay? Now, not that we've understood it all that well, but we've known about it. Especially sailors. Okay? When they're out at sea, nothing on the horizon. How do they know which way they're going? And yeah, well, they use stars and sun and ideas like that. But they found out there was a certain material naturally occurring that was called lodestone. That was the common name for it. Now we know it by the mineral name magnetite. Now what is magnetite? It's a form of iron ore. Iron ore is usually hematite. And magnetite and hematite are absolutely identical to each other chemically. Exactly the same. Looking at them, you can't tell. It's just that magnetite is magnetic and hematite is not. Okay, now, without going into too much gory detail, that comes from the fact that when you had volcanic eruptions and volcanic material was laid down, molten iron was laid down, if it was in the presence of Earth's magnetic field happened to be pretty strong right there where it was happening and laid down along those field lines, then the naturally occurring magnets were formed from that magma. If the magma was just very rapidly done and stuff and it mixed, it wasn't a strong Earth's magnetic field at the time, you got hematite. If it was along those lines, then you got magnetite. Now the surprising thing, as they've done cores through the surface of the Earth where they knew there was regular eruptions going on, they found out that there have been reversals in those magnetic fields 22 times in the last, seems like so many million years, okay, that they've been able to calculate the cores. And nobody knows why that happens, okay. It seems like the Earth's magnetic field shifts really, really slowly. Sometimes it's strong, sometimes it's weaker, and then strong in the other direction, weaker, strong in the first direction. It's kind of like a sinusoidal curve. Remember, we talked about that with waves. The thing is, the periods are enormously long. And this is like I said in my physical science class just, I think, last time. If you put the creation of the Earth back there when the sun became the sun and all the extra material became the planets. The Earth was created, and you put that in that corner, and you put modern history in this corner. Okay? All the time that mankind has been on Earth, knowing and using this information would fit in that last half block. Okay? So the 22 changes have occurred. We've just lived in one time when the magnetic field is pointing toward the north. Okay? And so that's why, I mean, all of mankind, I mean, this was prehistoric man was still on that last half block. Okay? All the rest of it, that's when those other layers were laid down. Okay, so you have naturally occurring magnets, but people found if they took that naturally occurring magnets, they were very valuable, and stroked another material on that, they could make another magnet. But not any material. There were only 3 metals known to man, and there still are only 3 known to man, that are naturally occurring magnetic materials. And I think I recognize this guy from somewhere. Good to see you. Okay. All right. And those 3 materials are iron, nickel, and cobalt. Okay? And it seems like we did find a periodic table somewhere in our book. I don't remember exactly where that was. But it seems like we did find one at one point. But I'm not going to waste time looking for it. I'm just going to see if it's anywhere obvious. But maybe not. I teach from several different books, so I don't know. If there is one, you'll find those 3 metals are right next to each other. All the rest of the metals are all around them. None of them will produce a magnet. Only iron, nickel, and cobalt. Okay? So, what if you do have a magnet? Or, okay, number 1. Let's pretend we do have a magnet. A bar magnet. North on one end, south on the other end. Just imagine this is one magnet here. Forget about the rest of it. Forget about the iron filings. If you have a piece of aluminum and hold up anywhere near that, nothing is going to happen. But if you have a piece of iron, nickel, and I've never had a piece of cobalt, so I don't even know what it looks like. I think of it's blue, but I don't know if it is. But that would be attractive. None of the other metals, copper, platinum, gold, silver, nothing would be attracted to the magnet except iron, nickel, or cobalt. Okay? So, those are the only magnetic materials. Now, just because they're attracted doesn't mean that, say, that paper clip would be a magnet. Not unless you struck it along there and then you could make it a magnet. But it would still be attracted. Okay. So let's assume that we have that known magnet. Okay. And by the way, they all have north poles and south poles. Every magnet has a north pole and a south pole. Try like you might, you will never isolate a north pole or a south pole. Now, we'll get to this a little bit later, because this illustration is for a different purpose. But you'll notice, even if these 2 weren't here, those pieces right here, all the iron filings are attracted here and here. Nothing is attracted here in the middle of that magnet. Well, let me get my saw out here and saw the magnet off here, and then I'll isolate a south pole, won't I? No. As soon as I do that, wherever I cut, that becomes a north pole. And this becomes a south pole. Every time. And if you think about it, those little refrigerator magnets you have, look how thin they are. One's a north and one's a south. Okay? Those are always occur. And we say that magnets are always dipoles. Now, I've had a few students call them bipolar. That's a disease. Okay? That's a mental thing. No, they're dipoles, not bipoles. Okay? They mean the same thing, 2 poles. Okay. Now, if I had one of these magnets like this one, ignore this one for now, and I had another thing that I knew attracted metal, iron, nickel, or cobalt, so it must be a magnet too. How could I tell? But it doesn't have an N or S on it, so how could I tell which pole was which? Well, I could bring one end of that because they're always dipoles. Bring one in, and especially if I let this one hang from a string, so it was hanging there freely, and I held it close to it. If it attracted the north, guess what? That's the south. If it repelled the north, this is the north. Then I can flip it over and do the same thing, and you'll find that always works. Like poles repel each other, unlike poles attract each other. Okay? So that's a rule for magnetism. Okay? All right. Now, why is that? Magnetic poles repel each other, unlike poles, magnetic poles attract each other. So a lot like electricity in that like charges repel each other and unlike charges attract each other. We did that when we were doing charges. Okay? Now, why is that true? Well, just like in electric charges, an electric charge is surrounded by field lines that emanate from it or go toward it. The rule for field lines for charges, where field lines go away from positive charges and go toward negative charges. Well, the same type rules apply. There are field lines around each pole of a magnet. The field lines emanate away from, this is just the convention, away from the North Pole and point to the South Pole. Now, you can't see field lines, you can't feel field lines, but you can visualize it, and that's what they use the iron filings for. Now, I wish they didn't have these here. In your text, they have something like this, but the magnetic field, and since they don't have it in the book, I'll just show you here. Put it up here. Can y'all see that? Okay? Okay. The field lines you visualize by emanating from the North Pole and moving toward the South Pole. Always. That's the direction of the field lines. You'll notice they're all concentrated there and concentrated here, just like we see here and here. These are iron filings, okay? And if you had put a bar magnet underneath a piece of clear vellum or something like that that's pretty thin, and then sprinkle iron filings on top of the vellum, look at that. The iron filings line up just like we visualize field lines. Okay? And that's what the iron filings are doing here. Okay? And this is leading, and you see the field lines of the North Poles would be emanating out equally in all directions. However, another North Pole, and because they repel each other, the field lines are pushing against each other this way. That is why like poles repel. Whereas, if you put the north near the south, the field lines attract each other. All the field lines group there, you see in between, you can't even distinguish field lines. But here, you see the iron filings are lining up like field lines. And by the way, these iron filings are like little pieces of they're not even little needles, but little pieces of things, and they all line up and hook onto each other a lot like a cobweb does. If you've ever taken a cobweb and touch it, it falls to pieces to thousands of little particles that just happen to line up with each other. Same thing here. These are thousands of little particles, but they all line up this way, and that represents the field lines. Okay? And notice when you have this, that is the strongest field line. You can't even distinguish them there. But these you see a little bit better. These are trying their best to get away from each other because like poles repel. Okay. Now, why do magnets point to the north, though? Because the Earth is acts like a big bar magnet. Okay? And that's what we have being illustrated here. Now, I'm going to give you a little bit of the physics of it that you don't need to know, but it really helps. A magnetic field is produced anytime you have a moving charge. A magnetic field is produced anytime you have a moving charge. Okay? Now, you have charges moving everywhere, right? Every atom is surrounded by, every nucleus of an atom is surrounded by electrons flying all around it. Okay? So why aren't they all elements magnets, naturally occurring magnets? All the time. Well, because let's say, give me an element, any element except iron, nickel, and cobalt. Say aluminum. Okay? Here's aluminum. It has electrons flying like this, like this, like this, like this, and the sum total is they all cancel each other's magnetic fields out. Even though each electron produces the magnetic field, they all go in random order, so there is no net magnetic field there. There's something about iron, nickel, and cobalt and their electron structure that each one of the atoms is a little magnet. Okay? Now, why is all hematite magnetite then? Well, because the individual atoms, this one will be pointing this way, this one that way, this one. See, the other elements don't have, their atoms aren't little magnets. Iron, nickel, and cobalt are, but they're pointing in random directions. So usually hematite is not magnetic unless you stroke it with another magnet. Okay? Then you can make it a magnet. Okay? Nickel and cobalt, same way. Why is that? Well, because by stroking it, you see, by stroking it, now, let's imagine this. What if you had a strong magnet here, and you had an iron needle that wasn't magnetic? You bring it close to it, then it aligns all of those things, and it becomes magnetic. But if you don't touch it, it just aligns them. You take it away, it's not a magnet again. They go back to the random order. But if you, okay, now this time we're going to move it over it but never touch it. Still doesn't make a magnet. But if you touch it and rub across it, now you're jiggling it, you're perturbing it. Now all those, what they call them are domains. All the atoms line up as much as they can. Not, they all don't do it, as much as they can, and because you jiggled them, now they get fixed in that place. Now they become magnetic. Just getting it close, they'll move, but then pop back. You think of it like elasticity. But once you jiggle it, it's no longer elastic. So, let's go back to the Earth. Why did that come up? Well, the Earth is spinning. Okay? Now, most of the surface of the Earth is water, but if you look at the surface of the Earth, sort of like we did history, if you looked at the surface of the Earth, the deepest part of the ocean would be, let's imagine we had a globe that filled the whole room here. The deepest part of the ocean might be that big, okay? Because it's not. Inside that is a huge ball of rock. But it's not rock all the way. Somewhere down there, in what we call the mantle, inside that is the outer core, which is molten liquid. That's where volcanic activity comes from. You know, molten material comes from down. Not that deep, but it comes from like that. Okay? And that molten core, as the rock is spinning, okay, the liquid inside doesn't spin as fast as the rock, does it? So you have the edges, and the rock isn't smooth. It's not a nice, pretty, perfect ball or anything. It's jagged and ragged and all that kind of stuff. And it's spinning, pulling the liquid with it, and you're knocking off electrons all the time. And guess what? That core is iron and nickel prominently. Those are the two major elements in the core of the Earth. Iron being the big winner, nickel number 2. And they are magnetic materials, knocked off electrons, moving charges, they produce magnetic fields. So that's why the Earth has a magnetic field. Now here's the weird thing. Our geographic North Pole, that's the center of the axis of our spin, it's not quite the same place as the magnetic North Pole is. Don't know why. Irregularities in that molten core, something like that. The magnetic core, North Pole, is over here just a few degrees off. I looked at it yesterday on a globe. And I'm trying to remember. It's around 15, 17, 18 degrees, something like that, off. Not far at all. Out of 90 degrees, out of 180 degrees, that's not far at all. You know, just a few degrees off. Now, the South Pole is even further off. It's more like 30 or something like that. So it's sort of far off. No, I think it was 25. Okay, so it's further off, but the North Magnetic Pole is fairly close. Okay, now, so the Earth acts like a big old magnet. Okay, and this kind of illustrates it. Oh, this is a great illustration. This, I think, is representing the solid core, and then the inner part is molten or liquid. But actually, the inner part of that is solid again, but that doesn't really have that much influence on it. It's that interaction between the solid and the liquid that is where we think we get most of the magnetism. Okay. All right. Anything else we need to do? There's really some interesting subtopics here, but I don't think we'll go into those now. All right. I think we're moving into 9.2. Yes. All right.
18.2.
19.2, I'm sorry. 18.2, I don't know. My brain is somewhere else, I think. Okay, 18.2. Okay. A man is mentioned here, Hans Christian Ørsted, born in Denmark. I'm not sure he did all his work there. I guess he did. But he was a physicist born in Denmark, late 1700s, early 1800s, basically about the birth of the nation. Okay, 1777, that's a year after, 2 years after, 1 year after we were born, 1776, and then up to just before the war between the states. Okay, so that was when he lived. And in 1820, he was the first to discover the connection between electricity and magnetism. Okay, I don't know if you remember back when we first started talking about electricity, it was known, things were known about it, that if you rubbed amber with wool or with fur, you could shock people, you know. Oh, yay, that's all they knew about electricity for hundreds of years. Well, magnetism, at least it had a useful purpose. It would point to the north. The needle would point to the north, or pretty close to it anyway. Not exact, but close. But no one made a connection between electricity and magnetism. They didn't seem like they were at all related until Hans Christian Ørsted. Okay? And what he found, by this time, we talked about some of these other guys. Alexander Volta had created the first batteries, so then you could create currents, which is flow moving charges. And what Ørsted found is that if you connected a battery but had the switch open so there's no current flowing through the battery, through the wires, put a compass over it, the compass is going to point north. Of course, that's where compasses point. But as soon as you close the switch, now the current compass points some other direction. And why in the world is that? Okay? Well, here's the reason. Take your right hand, and with the thumb of your right hand, point in the direction of the conventional current. Remember, the conventional current would be the direction a positive charge would move if it moved. We know that really it's electrons moving the other way. But that's beside the point. Point your right hand in that direction, and then your field lines go like that, and the way they point with the compass underneath that is that way. North would be pointing that way. It's not pointing to the north, but the field lines have changed. They've overpowered the Earth's magnetic field lines, which point that way, and now are pointing that way. Okay? Now, what if we, now this is hard to see, they've changed and put the positive here and the negative there, so now the current is flowing this way. Well, now your right hand with the thumb here, point your finger, and the ones going under the wire are now pointing to the north. That's the way the field lines are going. So the north lines up with that. Okay? That was C. Here's D over here. Open the same one as this one. Open that up, and the compass goes right back to pointing north again. Okay? Oh, and what we've done, we've also now put the compass on top of the wire, not under the wire. Here it was under the wire. Here it's on top of the wire. With the switch open, pointing north again. But as soon as you close the switch, your current flowing this way, the field line coming across the top are now pointing that way rather than this way. So you see you have field lines around the wire, and they go in a circular type pattern. Okay? Switch the polarity of the battery, so your positive side's here, your negative side there. So you change the thing across the top, right hand rule, there you're pointing that way again. Okay? So you see the field lines go around the wire. Anytime you have a moving charge, you induce a magnetic field.
I don't know what you were saying about
What's that?
the field line, but you're talking about the line coming from the positive and the negative.
Okay, no, the current comes from positive and negative. That's where your thumb is pointing. Your field lines go around that. Whichever way the current's flowing, your field lines go the way your fingers are going. The current is your thumb. The field lines, the magnetic field lines, are the current, are where your fingers are going. Okay, picture it this way. Have a sheet of paper with a single wire going through it. Okay, you put DC current. Can't use AC. If you use AC current, that's going back and forth, back and forth, back and forth, back and forth. So, yeah, you don't establish a magnetic field. Okay? But DC current, especially if it's a pretty strong current, through that piece of paper, sprinkle iron filings on the paper before you connect it to the battery. They just lie there randomly. You put a strong current through there, you'll see them form concentric circles, getting weaker as you go out, strong in the middle. Just like you saw the iron filings line up around the ends of a bar magnet, they go concentric circles around the wire, because that's what's happening. The field lines, your thumb is pointing in the direction of the current, and the fingers are pointing in the direction of the field lines, magnetic field lines. Does that make sense? Okay. A moving charge induces a magnetic field. Okay? The positive charge going this way, the field goes perpendicular to it. Positive charge going this way, the field goes perpendicular to it. But around the circle like that. Okay. Andre Ampere was mentioned, I think, in the last chapter as well. They named the current unit for current after him, amp, or ampere. He was a French physicist, mathematician and physicist. His work became the basis of the science of electrodynamics following Ørsted's discovery in 1820. And the SI unit of electric current, ampere, is named after him. So we've talked about that. The direction of the field near the current of a straight wire is called Ampere's rule, and here's what it is. Just what I was saying. Okay? Here's that wire going through a piece of paper. Okay? If you took iron filings and put on there, before you put the current there, they just lay scattered around there. You send the current through there. Now we're going to use a positive current, okay, going up the wire here, okay? Not really, but you know, imagine that. Then as soon as you connect it to a strong battery, then all of a sudden you get all those iron filings just lying there like this. Suddenly they go into circles, okay? Almost a continuous pie shape, but they're most concentrated here. You have the field lines going like this. That's the direction. That's what they're doing here. Put your right thumb in the direction of the current flow, the positive current flow, the conventional current. Then the field lines are going in concentric circles around that, perpendicular to that. Change the current, and they go in the opposite direction. Okay? So that's why the compass over here is going to point this way, but the compass over here will point this way. Change the current, and the compass here will point this way, and then it'll point that way on that side. And on the back side, it changes as you move it around the wire. The compass needle changes, always perpendicular to the wire. That's the right-hand rule, and this is Ampere's rule. He described it. Okay. Now, that's his rule. Here is the law that they base that rule on. Okay, are they going to show that here? No, they're not. Shame on them. So I'll write it here. Now, from now on in this chapter, B will be magnetic field, okay? And if you have it, E will be electric field. Capital B is magnetic field, and capital E is electric field. I don't think we'll hit that for a while. But here's what we have. The magnetic field, B, is going to be that good old mu naught. Do you remember that? It was called, oh man, permittivity of free space, I believe is the name of what that was. We ran into it back before, but it's mu naught. 4 pi times 10 to the negative 7. Okay, we'll get there. I'll write it in a minute. Okay. B is equal to mu naught times I, which is the current in amperes, divided by 2 pi, and then capital R. Well, that capital R is the perpendicular distance from the center of the wire. Okay? So in other words, if you were a very short distance, that's going to be a very strong field. Move a little bit further out, it's going to be a weaker field, because that's an inverse relationship. Okay? So that is your distance from the wire. Okay? And mu naught, I wish they had a table. Let's see, maybe they do. Magnitude. No. These are just formulas. I know it's in the book somewhere. I don't have time to look for it. Oh, here we go. Maybe. Nah, it's not here. Common physical data. They don't list mu naught. I thought they would. But you'll find it somewhere. Let me see if I can find it here. Permittivity of free space. Nah, not going to see it here either. Nah. This book is not organized in a way I like to do it. It has an organization, but it's not like most physics books I'm used to doing. So I can't find it, but I believe that is called the permittivity of free space. Okay? And mu naught is 4 pi times 10 to the negative 7th, and the unit is Tesla. That is how we measure magnetic field strength, is in Tesla, meter per amp. And of course that sort of makes sense because the current is in amps, so those will cancel out. This one's in the denominator for mu naught, numerator here, and then here you're dividing by meter, so you multiply by meter, and that leaves B being measured in Tesla. That's how we measure magnetic field, is in Tesla. That's the SI unit. There are some other units that sometimes are used. One particularly was called a Gauss, named after Johann Gauss, I think, or something. I can't remember his first name. But anyway, that's not a SI unit. That was a customary unit. The Earth's field strength is measured in Gauss. A Tesla is much stronger. Yes?
I have a question. It says, what voltage is required to produce a current of 2.85 A in the second below? Is it supposed to be a pitch or something?
Okay. I'm sorry. This has nothing to do with what we're talking about here, is it? Okay. What are you saying?
Yeah, it's about a second A in the second below.
Oh. No. Okay, can y'all remember on this fifth test, maybe y'all had this question too. Where is it? Here it is. This is this most recent test I gave you. Okay. The circuit below is the one that says, use the one that's right below that, 36 volt power supply, voltage, okay? E is equal to 36, and then you have those 3 resistors in it. So, no, I'm sorry, that's not it, because that tells you what voltage it is. Man, let me, okay. Oh, I'm looking at the wrong test. Okay, wait. Oh, here it is. Ah, here we got it. Oh, I see. Okay. No, use the same ohms. Ignore the 36. Right. Ignore the 36. Use those resistors there in series. So just add them up, and there's the current. And what voltage would be required to produce that current?
So add up 1.5, 3.25.
And 2.05. Okay, that's your resistance. Your current is 2.85, and then what voltage would produce that? Okay, sorry. Ignore the 36 volts, okay? But then on question 8, now you have a different voltage, 36 volts, and that's what you use. All right, sorry about that. Okay. Okay. Thanks for pointing that out, because I'd forgotten they left that off. Okay. All right. Now, Tesla. Who in the world was Tesla? Nikola Tesla. He was actually born in Croatia. Now, this was back when Croatia was Croatia. When y'all were young, I don't know if you knew this or not, Croatia was part of Yugoslavia. And after the Soviet Union fell apart, then the Soviet states, Yugoslavia being one, then had civil war and started breaking back into its earlier divisions, okay? Serbia is part of what was once Yugoslavia. Croatia is part of what was once Yugoslavia. And then there's another part called Bosnia-Herzegovina or something like that. Okay? And then there were a few other smaller parts. Let me see if I can remember this right. The Serbians, I think, were typically Orthodox Christians. The Croats or Croatians, I believe, are Roman Catholics. And the Bosnian Herzegovinians were typically Muslim. So there was, when it was Yugoslavia, it was ruled by a very powerful dictator named Tito, and he forced the groups to coexist together okay. When they had a chance out of that, they started fighting with each other, and there were some really bad atrocities that occurred during that war. It's called the Balkan Wars. You can read your recent history and find that out. But anyway, way before that, Nikola Tesla was from Croatia. He came to the U.S. and worked under a pretty famous guy, Thomas Edison. And Thomas Edison was one of the early inventors of electrical things. Is someone out there? Oh, there we go. Okay. Huh? Vaguely, okay.
Remember to bring the evaluation for me to sign?
Oh, goodness gracious. I forgot it again. I had so many students that, okay. Are you going to be on campus at all next week?
I will.
What, on Wednesday again?
Mm-hmm.
Okay, even though that's finals week?
Yes.
Okay.
I'll try to catch you there.
Okay. I'm so sorry.
I understand.
Okay.
I have to
Okay. Yeah. Okay. So anyway, Tesla worked under Edison, but Edison was convinced the future of electricity, and he invented so many things. I think he holds a record for the most patents of any individual. Incredible scientist, engineer, but he was convinced that electricity's future was in direct current electricity. He was afraid alternating current was far too dangerous. High voltages, very dangerous. Tesla was convinced otherwise. He said the only future we have is in AC, alternating current. Well, we use them both, but far more predominant is alternating current. They fought and disagreed, and Tesla ultimately broke away and worked with Westinghouse. That's a familiar name. George Westinghouse, who was more of a businessman, but anyway, he took off and did there. But still, Tesla had so many great ideas, but wasn't a good businessman, and I think he died a pauper. It was sort of shameful, but he invented so many things. He was so much right on the money with so much, and wound up losing it. Okay, not being very famous, but not very rich because of it. Okay. So that is Ampere's law. Ampere's rule is the right-hand rule type stuff, but Ampere's law is that this is the strength of a magnetic field. Okay? Now, that unit is Tesla. There is another thing that we talk about, and that's called magnetic flux density. And we're not going to get into all that, but magnetic flux is a symbol called phi. I'm not going to write with that. Okay. Phi is magnetic flux. And this isn't all that important, so I wouldn't get overwhelmed by it. And divide that by the area, and that gives you your field. So you can refer to the magnetic field as the flux density per unit area, the magnetic flux per unit area. All right, so let's try to do example 1 based on these. And since I have it written here, let's see if we can use this screen, unless this is too busy for you. I can go to a clean page if you want me to. What you think? Is this too confusing? Okay. Example 1. A power line carrying 400 amps. What's that a measure of? Current. I is equal to 400 amps. And all those zeros, both zeros are significant. Okay? Is 9 meters above a transit used by a surveying student. Okay? So what would that be? 9.00 meters. That would be, in that formula up there, Ampere's law,
R.
that would be your R. That's how far it is away. So the power line's 9 meters up there. Now, just to give you an idea, I'm about 2 meters tall. That makes the room about 3 meters tall, right? Because from here to the ground is about a meter. There's another, I'm a little less than 2 meters tall. Okay? And then you could put another half body above mine. I'm not going to say whose body you cut in half, but whatever. Okay, and that would be about 3 meters. So we're talking about a 3-story building. 9 meters would be 3 stories of the building. So if this is a 2-story building, put another thing. So that's how far the power line is up there. Okay, and you got 400 amps going through the power line. 9 meters above the transit used by the surveying student. Okay, the A part of the problem here says find the magnetic field formed by the power line above the transit. Okay, so what we're looking for is B. And B would be mu naught, which is 4 pi times 10 to the minus 7 Tesla meters per amp. Okay, mu naught times I, which here was 400 amps, divided by, whoops, I went through my A down there, 2 pi times r, which is 9.00 meters. Okay? Now, if you notice here, this a cancels that a, this m cancels that m. Actually, pi cancels pi, and 2 will go into 4 twice. So you got 2 times 10, goodness gracious, 2 times 10 to the negative 7th times 400 is, okay, you got calculators, do it. 2 EE or EXP negative 7 times 400 divided by 9. And what would be your magnetic field strength? 2 EE or EXP negative 7 times 400 divided by 9. What you get? Second? Okay. Anybody? 8 point what? 89 negative 6 Tesla. Okay? Now that sounds pretty weak, but it's about equivalent to the Earth's magnetic field line, field strength. So it's not that strong, but it's not super weak either. A compass would probably be affected by it. Okay? Now here's the only thing that's a little bizarre about the problem. Most of the time you don't have power lines carrying direct current. Okay? They carry alternating current. So this is kind of a made-up problem. So if you did have direct current up there, that would be the field strength. Okay? Now the B part. I'm going to put it up here because I don't have room down there. The angle, okay, the angle that the resultant vector, the Earth's field plus the wire's field, that's B sub E and plus B, makes with BE would be the angular error. Wait a minute. Seems like something's missing here. I didn't read the thing. Okay, here. I missed the part of the problem. Back on example 1. If the Earth's horizontal component of the magnetic field is 5.20 times 10 to the negative 5 Tesla, so you see this is actually a little bit weaker than that, at that location, what error could be introduced in the angular measurement? Assume that the power line runs north to south. Okay? Now that we haven't approached at all, and I think it's a little bizarre that they would give us this problem here. But I'll just show you what is meant by that. If you've got your book, here is the figure we're supposed to be somehow knowing about. Here's a student down here with the transit, and here's the line up here with the direct current going through it. Strange. Three stories above his head, above the transit here. The field lines are going like this, and the B for the Earth is in the same direction as the line here, because it said assume the line is going north-south. The B for the power line is somewhat perpendicular to that, okay? So there it is, and that's shorter because this is 8.89 times 10 to the minus 6, whereas the Earth is 5.20 times 10 to the minus 5th. So this is a good bit longer, but perpendicular, so the resultant would be there. And what was the question? Okay, what is the angle? If the Earth's component of magnetic field is at the location, what error would be introduced in the angular measurement? Okay. If he's trying to measure Earth's, I think that's what it means. He's trying to measure the Earth's field, but this is distorting it somewhat. What would be the angle? Well, that requires trig. And y'all haven't had trig necessarily, have you? No? Let's forget that. I won't be asking you one like that. Knock on wood. Okay? Who knows? But we didn't. But just for the general information, put this up here again. The key here is that it is a right angle there. And if that is a right angle, this is the angle theta that's introduced by that small magnetic field produced by the line up there. And that length is the same as this length. There's, again, your right angle there. And the angle theta here is the tangent of this angle is its rise over its run. In other words, b divided by b sub e. So that's how they get the tangent theta, and then you do an inverse tangent, which is on your calculator, but y'all don't need to know that. Y'all don't need to go there, okay? And we will proceed from there. So that's how they do the rest of the problem, but because y'all haven't had trig, I'm not going to hold you to that, okay? Now, the error could be 9.7 degrees because of the power line. Student didn't realize he was standing under a power line. Okay. Some student. Okay. Yes.
Oh, I gotta go catch the cafeteria before it closes.
I'm sorry?
I said I gotta go catch the cafeteria before it closes.
Oh, you have to? Okay. Okay, let's see how we're progressing. We got another half hour. Okay. Okay. The test that we have, you can do number 1. You don't have it yet, but if I do give it to you. You could do number 2. We're going to have what you say we just go with electricity chapter being the last one you'll be tested on. Because I don't think we're going to cover enough material tonight because we only got 30 more minutes to do more than 5 questions. And that would be a pretty tough for you to do that. So let's... What's that?
So the one that we're working on now?
Yeah, that'll be your final exam. But I do want to expose you to this in case you need it in the sonography program, okay? I don't see how you could, but in case you do, I want you to be at least have been exposed to
So
it.
what's the final exam?
What's that?
What did you say was the final exam?
The one you just turned in.
Okay.
Yeah. You did turn in yeah, okay.
That's good?
Yeah, okay. So we will not have another test, okay? All right. So y'all are still working on that one, right?
Yeah, well, yes.
Okay. Okay. So you don't mind having that as your final? Okay. So you can either get it to me between now and next week, or I'll be here next week to pick them up. You can come in anytime between 4:30 and 6:30. I'll be here grading papers like crazy. Okay. Okay. So let's continue with this. Because otherwise, I just don't think... It just doesn't look like we're going to have time to get enough done to make a decent test. So let's continue. All right. So do y'all think you're going to need things like the angles and stuff like this? Do you have any idea? Okay. They don't require trig as part of the prerequisite for this, so usually they do for physics, but I don't think they do for the sonography program. So I don't think that's going to be required. So I'll forego the B part. Though it's a pretty simple thing to do, but your calculator does all the work. So let's move to the next topic here, and that is that of a solenoid. Okay. Now, Remember we said a single wire with direct current flowing through it produces a magnetic field. That's a very weak field. But what if we take that wire and make a loop out of it? Now, all along that wire, okay, let's say the current is going in this direction, the field is like this, all the way around. So in the middle of the loop is a north pointing, and the bottom of the loop is south pointing, and all that loop is reinforcing itself. So now you've made a stronger magnetic field in the middle than you have. You have a little one on the outside, but really strong in the middle because all that points up and toward the middle. Okay? Hey, we've just increased our field strength. Hey, how about let's doing several loops? Now they're adding up because they're all, as long as you don't turn the wire backwards, then you're all adding up. So now you have a very strong field. That's what we've got going on here. If the current is going up this way, okay, and the coils are in this direction, notice your right thumb is pointing in the direction of the north pole. You make a magnet without there being a magnet there, okay? This is called a solenoid. Magnetic field of a core, and if you put the iron filings there on the paper and run the coil through the paper like this, there's the bottom half on the other side. Look at those iron filings. They're showing you the magnetic field lines just like this. That's the north, there's the south, if it's lined up this way and the current's running that way. Okay? The coil of wire passes repeatedly through the white surface, and the compass is always also detect. So here we have the coil down here, okay, called the solenoid, and this is really hard to see. Hopefully in your book it's a lot easier to see that the compass needle is changing how it's pointing all around here because of the field strength around that core. It's sort of hard to get the compass inside the coil. That would be the strongest place, but that would be, that's indicating that you have a strong magnetic field there. Now the key here is that by turning on the current, you have a strong field, and turn off the current, it disappears. There is no field when there's not a moving charge. So this is how things like, you know, I think I do feel air and it's very cold. I thought they just didn't have the air conditioning on. I mean, the heater on. They have the system on, but the heat is not there. Okay? So, this is how they do things like, I was going to say, a thermostat. A thermostat is a very sensitive vial of mercury in there and a bimetallic strip, and when it tilts one way, then it will make the connection, and then just a little bit of a current there will produce current, you know, it touches two contacts together, current flows, and then your heat turns on, or your AC, depending on which way it goes. And that's how it works in the thermostat, and many other devices like that. That's probably how your remotes work. You press a button here, it sends a signal there, a little thing connects, and then that forms a switch, and then your TV cuts on or off, or the volume goes up or down. All these things are done with things like this, solenoids, or other things like that, that just a little bit of current can operate a switch. Okay? Because it sets up a magnetic field. Okay. A coil of tightly wrapped wire is called a solenoid. Okay? And it says, hold the solenoid in your right hand so that your fingers circle it in the same direction of the curve. The direction your right thumb points is the direction of the northern orientation of that magnet, the magnetic field produced by the solenoid. Just like is shown there. Okay? There's another example of the good old right-hand rule. For a long coil that is tightly turned, meaning the things are real close together, that's sort of tightly turned. That one definitely is not tightly turned. But for a long coil that is tightly turned, the field strength at the center is this. This is for a solenoid now. I don't think they show it here. No. Okay. Here's the field strength for a tightly wound solenoid coil. Okay. B is equal to our good old mu naught, the permittivity of free space, times I, that's your current, times N, which is the number of coils. This one would have 1, 2, 3, 4, 5 coils. Okay? This one here would be where to count? Sorry. Okay. 1, 2, 3, 4, 5, 6 coils. Okay? This one would be 1, 2, 3, 4, 5, 6. Okay, as many as you got. Okay? And you can have these really tightly turned with many, many coils. Boy, that can build up the field strength pretty quickly. Okay. Number of turns. Oh, wait, I'm sorry. That N is not the number of turns, it's number of turns per unit length. So N is number of turns per unit length. Okay. That's slightly different from just number of turns. Okay. So let's do example 2. Find the magnetic field at the center of a solenoid that is 0.425 meters long. So that's going to be the length is equal to 0.425 meters. That's just a little under half a meter long. That would be 15 inches, something like that. Okay? And 0.0750 meter in diameter. Okay? Where does that come from? Okay? So the diameter is 0.0750 meters. Okay, that's 3 significant digits, that is. Okay, nothing in what we have written here has anything to do with diameter. Okay, so why are they even giving us that information? Well, I guess we'll see. Okay. All right. Has 3 layers of 850 turns each. Okay, 3 layers of 850 turns each. Okay? Okay. Still don't see. Okay. When 0.25 amps flows throughout. So the current I is 0.250 amps, a quarter of an amp. Flows throughout the coil. Okay. Now, so we've got that 0.250 amps. Now, the number of turns per unit length. Okay, we have 3 layers of 850 turns, so that would be 3 times 850. That's the number of turns per, and the length here is 0.425 meters. Okay, that's going to be a lot of turns per unit length. Okay? And that's it. See, we don't use that other information at all. Okay? So, what is the B? The B would be then mu naught is 4 pi times 10 to the negative 7 Tesla meter per amp times 0.250 amps, that's your I, times this thing, which is 3 times 850 divided by 0.425. Okay, and this is your meter part, okay? The others are just turns, and you see the meters are going to cancel meters and the amps are going to cancel amps, okay? So, pull out your handy-dandy calculators and see what you got. There's no 2 pi to cancel out the 4 pi, so you're going to have to use 4 pi EE or EXP 10 to the minus 7 times 0.250 times 3 times 850 and divide that everything by 0.425. This is number of turns per unit length. So that's your N. Should be a pretty decent sized number. Well, okay. This is 10 to the minus 7, so it's going to be a lot smaller, larger exponent than that. It'll still be negative, but it's going to be like 4 orders of magnitude better. So what would that be? 1.88 times 10 to the negative 3 Tesla. Okay, now remember back, the last one we did, we had the magnetic field line from that power line 3 stories up in the air to be about 10 to the minus 6 Tesla. The Earth's magnetic field was 10 to the minus 5 Tesla. This is 10 to the minus 3. This is 100 times stronger than the Earth's magnetic field lines. This will really make a compass go crazy, okay? It's not going to stand the chance of the Earth's magnetic field taking over from that. All right. Yes?
The book got times 10 to the negative 3, but I've done it twice, and I got 1.88 times 10 to the negative 2.
10 to the negative 2? Okay. All right, do this. 3 times 850 divided by 0.425.
About 6,000.
6,000, okay? Let's just take a look at this. Okay, 4 times 0.25, that's a quarter. 4 times a quarter is going to be 1, okay? Okay, you got 6,000. Those 3 zeros will wipe 3 of those zeros out, so that would be 10 to the minus 4. So then we have pi times 6. Pi is 3.18, so that's 1.88 makes sense. So, seems like to me it should be 10 to the minus, wait. Oh, wait, no, I'm sorry. Pi is 3 times 6 is 18. So it'd be 18 times 10 to the minus 4. So this should be 10 to the minus 3, it looks like. So let me watch you do yours. Okay. Okay. Go back to the 4 pi. Okay. Now do. Okay. Use this EET first.
I tried that and it wouldn't do anything.
Okay. Do an equal and then do the EET. Okay.
It's still, I had to do 10. I had to do times 10 EE. Like if I just do EE.
Okay, no, okay. That's where the problem is coming. 10 EE. You see, you're doing 10 times. Do 1 EE. That's what you do. Yeah. It's done. Okay, I wasn't watching what you're doing. It's 1 EE because that's your exponent. You're doing 10 EE, so you moved it over one more space. Okay, that's where that came out. Okay. Now there's some problems there. If you feel like you need to know something about magnetism, those problems should be good for you. Odd 1 through 13. Okay. Let's see what's next. Induced magnetism and electromagnets. Okay. What we mean by induced magnetism, okay, is produced when a magnetic material such as iron, in a magnetic material such as iron, when the magnetic material is placed in a magnetic field. Now, we really already talked about that a little bit before with our iron filings. You put those iron filings in a magnetic field and beep, they all line up according to the field lines, right? I don't know if you've ever seen that happen, but
Remember that toy
yeah,
that had the man's face on it and it had the little magnetic stick
right,
and it had the little filings
right,
and you held the stick above it and you could, give him hair and a mustache.
right. Okay,
That's what that is.
that is exactly what it is. Okay, and in reality, in a much smaller scale, do you remember the old Etch-a-Sketches? Okay, wherever you did the thing, yeah, you're lining them up and then they all line up in the same direction. Now, you can't see them do that, but that's exactly the same type thing. Yeah, those iron filings, when you put it in the presence of the magnetic field, there they line up that way. That's what a piece of iron, a tiny little piece of iron in a magnetic field is going to line up according to the field lines. You've induced magnetism there. You take the field away and they go back to being random pieces of iron filings. That's all. Now, what an electromagnet is basically take a solenoid, a coil of wire, and put an iron core in it. And now you've got a really strong magnetic field with an iron there, and now that iron core becomes a magnet, as long as its current is flowing. Turn the current off, and it goes back to being random again. Okay. Now, what would be some uses for that? I've not seen this, but I've seen pictures of it. A big shipping port like Mobile, Long Beach in California, most of the big cities on the East Coast, okay? If they have ports that they can take these big container ships, in the old days, they had the longshoremen or whoever it was down there, whatever they're loading up, they had them on pallets or canvas or something like this, and they had to hook the hooks to them and the things, and the crane would pick them up and carry them over and load them on the ship, and someone had to unpack them there. Boy, what a labor-intensive thing that was. And if you didn't get things balanced right, something could tilt, or when it swung, something could fall out if you didn't have it secured right. It was a pretty dangerous situation, too. Nowadays, what these trucks do, these big tractor-trailer trucks, they have the metal trailers on the back, iron, and they go down, they pull up, they have an electromagnet come over, put it down, turn on the juice, picks it up, magnetic, moves it over, sets it down on the ship, does the next one. No tacking, no tying, nothing. One operator doing all that. Big old loads. Electromagnets are really, really strong. And you turn them on, you pick them up, turn them off, set it down. I mean, it's done. Okay? Now, I had a student in my class yesterday, older than I am, believe it or not. He said, but they always have a permanent magnet backup just in case the power goes off when they're transporting that. I did not know that. Okay, that's interesting. I don't see quite how it works, but it's interesting. Okay. Now, we talked about why magnetic materials are magnetic and others are not. This is basically what I was talking about. This is iron, or nickel, or cobalt, but none of the others. Every one of the little magnets, every one of the little atoms in there is a magnet. but they're randomly shaped, so all the magnetic fields cancel each other out, okay, when it's not magnetized, okay? Okay? Now, you put it in a slightly, in a weak field, say, just in the presence of something like a single wire going through the thing. Then, rather than being completely random, notice you see here you have about as many pointing this way as you do that way. But put them in a magnetic field, a weak magnetic field, and you have more pointing to the right and fewer pointing to the left, so you create a weak magnet there. There's little iron filings lining up around the wire or something like that. Put it in a strong, like a solenoid core, which is 100 times stronger than the Earth's magnetic field lines, then put it in there, ching, ching, ching. They never all line up this way. Probably wouldn't be able to hang together. They would be repelling each other too much. But more of them do, and you can form a really strong magnetic field. An electromagnet can be, I think, thousands of times stronger than the strongest permanent magnet. Okay? They are really, really strong. That's why they can pick up the whole tractor-trailer bed. They don't take the truck on there, just the bed and the trailer part, and load it onto the ship, and off they go. Okay? These are called the domains. Okay? That term is used, the magnetic domains. Those are little groupings of atoms that line up in the same direction. Each arrow would represent one domain. Okay? When they're random, there's no magnetic field. They're not magnetized iron. Okay? But put it in a weak magnetic field and you make it into a little magnet. Put it in a strong magnetic field like a coil, and suddenly you have it. This picture here is another example of a electromagnet. Here it's picking up scrap metal. Okay? If you ever go to a junkyard, not that I think any of you would be going to a junkyard. Yesterday I was teaching a whole bunch of automotive students, and I said, "Hey, have you ever been to a junkyard?" Most of them raise their hands because they could pick up used parts there or whatever. Okay? But most of us probably wouldn't wind up going there much. But sometimes in those places they will take cars and crush them into a rectangle, and then they just take an electromagnet, because most of the cars made out of iron, pick up that thing, load it onto a train bed, a truck bed, whatever, and then haul it out of there. Sell it to China, or Japan, whoever, you know. That's usually where the scrap goes. But it could go to an American plant that's recycling too. Okay. So that is what we mean by an induced magnetic field. Okay? Ooh. They've skipped a lot of slides here. This is way over a couple pages. I'm going to just sort of as I said before, what produces a magnetic field?
Charge.
Moving charge. It has to be a moving charge. Okay? Now, on the other hand, you can use a moving or a changing magnetic field to induce a current, which is charge. A moving charge is a current. They go both ways. And like we said, electricity and magnetism are deeply connected to each other. The surprising thing is how cleverly they're done. And that's exactly what's happening. Now, I wish I had a figure of this. I don't. My other text I taught from yesterday did. If you had a magnet, a bar magnet, and you had a coil of wire here, and the coil of wire was connected to an ammeter that measures current, no battery involved any of this. You take that magnet, you've suspended, you've got one end tied up here, and you lower it through the coil of wire. When that north pole of the magnet goes through the coil, you'll see the current jump up. Okay? As the south pole goes through, it goes the other way. You pull it back up, South Pole moving up in the opposite direction, it does it this way, and then the North Pole moving up. So you can create an alternating current by just doing that. Okay? Huh. Interesting. So what do? We have, on many of the rivers in Alabama, hydroelectric plants. The water turns a turbine. Okay? That has an axis that turns what they call I can't think what that thing is, but anyway, you turn a magnetic inside a magnetic field. Strong permanent magnet here, north here, south here, strong magnetic field lines here. You turn a coil of wire inside that. Now here, the wires are cutting a lot of field lines. Here they're not cutting many. Here they're cutting a lot, but in the opposite direction. And if you turn that in that strong magnetic field, you've got current flowing through the wire. Alternating current. And that's how they produce electricity. Okay? Now, it doesn't have to be a hydroelectric plant. It could be a steam plant. That plant could be burning coal, producing steam through a steam turbine, turning, and you're producing electricity that way. It could be natural gas, making steam, burning the natural gas, making steam, turning the turbine. It could be a nuclear power plant. The nuclear plant is producing a lot of steam, and that steam is turning a turbine, and you're producing current. That's how we manufacture electricity. You've got to have a moving coil inside a strong magnetic field. And those power plants, somewhere down there in the dam, those are strong, huge, old permanent magnets there, and you're turning whatever is producing that. The dam, the water going over the dam, the steam that's produced however you produce it, that kind of stuff is producing AC current, AC electricity. That's how we do it. And then they ship it through the wires, get it to your home, and you use it. Okay? That's what is happening. This is called induced current. A current that's produced by a changing magnetic field. And the change is occurring because the coil is cutting the different numbers of field lines in different directions. So it's positive, negative, strong, weak, and that makes induces a current. Okay. So why they have the electromagnet on the same page as that, I don't know. Because, see, induced currents are most of the time AC, whereas the electromagnets, as we mentioned before, have to be direct current, okay, to form the electromagnets. Okay. So what we've just described are generators, and unfortunately, that's the end of our time. Yes?
I just wanted to ask a quick question about the last test
Sure.
you gave us, the most current one.
Okay.
On number 4, I don't know if I'm missing something.
Okay. All right, number 4. Okay, this is the, okay, let me make sure I'm looking at the other thing. Find the resistance
Yes.
of 845, I can't read, feet of number 4 copper wire if it has a resistance of 0.0262 ohms per foot.
My question is, we're not given the cross-sectional, we're not given the A in that problem. Is there a chart?
Okay.
I didn't know if there
Oh, it gives you how many ohms per foot, and it tells you how many feet.
Okay.
Yeah, that's all you do. That's not totally asking everything the book told about, but yeah, that's all it is. Interesting problem. Sounds really complicated and turns out being fairly simple. Okay. All right. Any other questions? Good questions, by the way.
Well, I do have one more
Yeah.
question. I know when we started this class, you said that you would drop our lowest grade.
Right.
I know we're only going to have 5 test grades.
Right.
Will you still drop?
I'll average the highest 4 tests. Okay. Or I'll count the 6 tests as your lowest score. How's that? No, I'm just kidding. Okay. Okay. The one we didn't have. Okay, no. All right. Sorry about that. We didn't get that quite as much covered. We came close. I didn't know we'd get that far along, but there's still much of what's on that test was in the part we didn't get to, so let's just forget it and go with this. Do y'all feel cheated? You want a refund of some of your tuition dollars?
I don't feel cheated. I want to know how magnetism is important. Do you know what I mean? Like,
Yeah.
that's the only.
I just could not figure out, if y'all were doing nuclear magnetic resonance, electron spin resonance, or any of those other things, yeah, magnetism goes into that really important. Frankly, for sonography, I do not see how it does. Okay, so I don't know. I'll talk with this lady hopefully Friday. Okay.
The last one you gave me, I'm still working on that one. And was there
Okay.
another one after the one that
Okay.
I waited on again?
Well, okay. I don't see one on the frequencies. Do you? Is that the one
I
you're
think
working
that's
on?
one I have.
Okay, so then after this was the electricity one. So you don't have that one, is that right?
Yeah.
Okay. Let me get the electricity one. That's the frequency. Oh, and if y'all didn't get your, here it is. No, that's the frequency
Yeah,
one.
I got that one.
Okay. That's it. Okay.
Thank you.
All right. Y'all want your test back. Okay. Jennifer already left, didn't she? Anna. Cora. I'm sorry I can only give the first 2. Okay. Kobe. Rachel. I guess she just left. Jennifer. There's your first one. And are you turning in the last test? Oh, you're not. Okay. You're going to wait. Okay. Okay. Jennifer. Cora. Cora. Yeah, sorry. Okay. Kobe. Jennifer. Okay. All right.
Yeah. I left out 30 ago.
Okay. The others, I have so many out, I'll just turn them back to you when you turn in your final. That's why I thought if you were going to turn in the last one today, I could only give you all of these.
So
Okay.
we can keep these.
Yeah, those are yours for keep. But don't let anyone see them because maybe some who haven't, but most people have.
I missed the test from the last
Oh,
period.
second,
I didn't get the test from last class.
from the electricity part. Okay. Wish I'd asked earlier. I just had them at my fingertips. Whoops. That's not it. That's it. All right. Yes, sir.
I forgot what chapter it was, but the first question was find the period.
Okay, I can't hear. Sorry.
Find the period of a wave with the frequency of 40.
Okay, and what about that?
I didn't get that one.
That test?
Yes, sir.
Okay. That one?
Yes, sir.
Okay. Now, the corrections on it were they didn't give us a frequency for the, what was it, a horn or whistle, that's 585 hertz.
Yes, sir.
And then down here it was a blare, it's a horn, that's 5,000 hertz.
Yes, sir.
They did right up to it.
Were we able to get to a printer?
What's that?
Were we able to get to a printer?
Oh, yeah, I've made copies for quite a while now, yeah.
Okay.
Okay, what do you need? Do you remember?
I think that the only 2 that I had, I ended up throwing away.
Why did you do that?
I don't know.
Okay. Let me see if I have any more.
And
Okay.
so I've been, I saw a tutor today in that math, for my math, and I got most of that first homework done, but not probably well enough, not that I would do very well on a test right now. But, so I'll be there to, how many homework or like, how many quizzes was there for the math?
2
3.
quizzes, 2 tests,
And then a
and then
final?
we're going to have, okay, you're in, is it 100 or 112?
112.
You're in 112. Okay, 2 quizzes, 2 tests, and then you'll have the last chapter we're working on now, chapter 3, there'll be a very short test on that, which will be less than an hour to do that one. And then the comprehensive really short, that'll be less than an hour. That's going to be your final exam. It's going to be a
Tuesday
last
or
chapter
Thursday?
test and a final test.
Okay, so I'll
That's-
get those quizzes done,
Right.
and then when is the final? Is that
Tuesday.
on Tuesday or Thursday?
Tuesday. Are you graduating this term?
Yes, sir. Trying
Okay.
to. I'll tell you when at the beginning of the semester, I told you that I had to change my major so I could graduate this semester.
Right.
So I was at Miles today applying,
Right.
and I tell you, I'm not. No, that's not it. So like I got a so Miles doesn't even accept some classes that Lawson gives. Plus, my major is elementary ed, and of the, I think 67 hours passed here at Northwest Shoals and here, they're accepting like 32. So I'm gonna still have 89 hours. And I was like, I asked about what if I had changed my major, and they were like, well, those classes you took, don't go to any major. So I was like, why are they offered? Like, why is general studies even a thing if
Okay.
the core classes? So I basically, this semester was, I wasted time on several, so I was pretty disappointed in that. But what I can do is I can get those, I've got the 2 quizzes. I can get those done.
Okay. Now,
And then-
if you're graduating this term,
Yes, sir.
I have to have everything in. By next Tuesday morning, because your grades are due in by Tuesday at noon. So I have no flexibility there. They have to be done. You have to take that last. You have to take
what
the
would
2
be the
tests.
best way to take those 2 tests then before I go take the final?
Whenever you can. I'll be on Bessemer campus tomorrow. We have class tomorrow morning from 8:30 to 9:45. You can take them right after that if you have time then, or whenever. But you have to turn the quizzes in before you can take the test.
Okay.
Okay. That's Thursday. Friday, I'm not here on Birmingham because the building had a fire in it, and so I'm on Bessemer. So I'll be on Bessemer from 8 to 12 on Friday, and you can take them then. I'll be on Bessemer Monday. I have a review session with a class from 8:30 until 10:20, or basically 10:30. And then anytime after 10:30, you can take them then. And then you have to take the final exam Tuesday morning.
I'm trying to think, because I've got some other things to do too. I just don't know that I'll be able to learn the material quick enough. So hopefully I can just make good on the quizzes, and then hopefully have enough on the worksheet on the scrap paper or whatever that I can muscle a few of them out.
Another option, then you wouldn't graduate, but another option would be take an incomplete
and
and
then get a couple weeks. I don't.
When were you planning to start it, Miles? This
in
January? Okay, well, you got to get it done.
So there's no way that the incomplete wouldn't work.
The incomplete would work up until I get the other grades in, which would be the following Monday. So you have another week to play with.
Okay.
But you probably.
So what I'll do for sure is I will email you over the weekend, and then Monday I may try to come take some tests. But tomorrow I'm gonna try to learn this stuff tomorrow pretty well.
Okay.
Because there's a Coach Jill, the volleyball coach, was a high school math teacher,
Mm-hmm.
and she had helped me in the past, so I can see her some tomorrow. The problem is, so what percentage of those 2 quizzes count for?
Really fairly low. Now, you haven't done a research paper in that course either, have you?
No, sir.
Okay, you got to do that.
How much is it?
Okay, well, here's how it works. The research paper and the 2 quizzes, okay, all right. I average them together. If one of the quizzes is below the average of the 3, then I drop the lowest quiz. If your research paper is the lowest and the quizzes are pulling up the research paper, I can't drop the research paper. That's a requirement. So that counts as a replacement. That counts as a test score. Then you'll have 3 tests, Chapter 1, Chapter 2, and Chapter 3. If your quiz average is higher than your lowest test score, I replace it. I put the quiz average instead of that lowest test score. So therefore, I drop the lowest test score. Mm-hmm. The final can't be dropped, so I average them all together. If it helps to drop the lowest test score, I do. If it doesn't, then I keep it in there. So it's sort of hard to say because it varies according to what's your lowest average, So
this is probably asking too much. Tomorrow when I have Coach Jill should be helping me with the quizzes.
Right.
Is there any way that I could take my test with her tomorrow, like after I went over the material? That way it's kind of fresh to me.
Well, the trouble is she doesn't have it. Is she on campus?
She will be tomorrow. Yeah, like she's up here all day. Now
okay. I thought she said she was a high school math teacher.
No, she used to be. She's
a
volleyball coach.
Right.
So,
okay.
The reason I got close with her is she was over study hall last year.
Right.
So she had helped me with math. She helped me with some English. She helped me with a number of things last year. So me and her, like, she's somebody she's always been able to help me with things. I'm actually going to have her revise a paper with me tomorrow too. So it's,
all right.
I just, I don't think the math is over my head. I just think that it's so much right now, and I've had really this semester. I knew it was going to be hard, and it got away from me quick. And if there's any way that I could take those tests as I'm learning it, like after, and I could have her sign off that it wasn't like I'm just sitting there on Google and using the app or whatever.
Okay. So are you suggesting that I email her a copy of the test? Or she administer it?
If you
I don't have it with me tonight.
Or if I could get it from you tomorrow, I could get it from you in the morning, and then I could have her sign it. Before
you see, I don't let others take the test off campus.
Oh, I see what you're saying. So I'll talk to her and see if she'd be willing to let you email her a copy of it. That way she can. I don't want it. Which you protected yourself with that, but I didn't want it to be like in the back of your head, well, he was just doing it with his phone or whatever. So, but I just need. I want to be able to do. To be honest, a D gets me out, but I'm not the person.
A D doesn't transfer though.
Yeah, I'm not trying to make a D.
Okay.
So.
Okay. Now back to your issue on Miles. See, Miles is a private school. Mm-hmm. They're not required to take anything we offer. They just decided they'll take this, that, or that other. A state school, University of Alabama, UAB, Huntsville, wherever, A&M, Alabama State, any of those that are state schools, they basically we're in agreement with them. If we teach it, they'll take it. If it's covered in the degree plan. Yeah, so that's why they would cover it, but Miles isn't required to.
If I wasn't this far in and I knew what I knew today, I probably wouldn't have decided to play baseball at Miles. I probably would have went elsewhere.
Right.
And because the other school I thought about going to is NAIA, and I was eligible to go there. Mm-hmm. But this I thought was better, and in all it might end up being better because of my living situation stuff. It was, and I've enjoyed being here, but it's like I'm looking at either being a student the rest of my life.
No, it's not the rest of your life. Another year or two.
Taking a whole lot of classes.
Right.
Even in the summers, like 15 hours in the summers. So
yeah.
But it's part of it. Now I'm trying to graduate, and I'm already 23. Like I've had several jobs that I didn't want it to be a career. So it's I'm doing what I got to do to get through.
Right.
But like this math, this is the last math class I have to take. So I'd really like to I'd really like to end up with at least a C, and I do. I think I'm smart enough to learn it if I had time. And I might end up having time. So yeah, like Friday, I might try to take test 1 or whatever. I'll kind of see about that tomorrow. But I guess I'll see you. I'll at least swing by about the end of the class and talk to you because the stuff you'll be going over tomorrow is not the stuff I'm trying to learn right now. Well,
but you need to know it for test 3 and the final.
Yeah. Yeah, I need to be there in the morning then. Yeah, so I'll talk to you tomorrow, and if I can get quiz 1 done, if I could take test 1 tomorrow during class,
All right.
or something like that. But I'll see, because I've got I got a paper I'm going to type tonight, and then I'll kind of see what's after that.
Yeah.
But
Is that my paper or a different paper?
It's a different paper.
Okay.
So your research paper was worth how much?
It's a quiz score that can't be dropped.
Gotcha.
A 0 on that,
What was it on?
huh?
What's it
You
supposed to be
choose
on?
your topic. Anything to do with math.
Anything to do with math?
Yeah,
Okay.
applications, whatever. Has to be 1 to 2 pages of word process, double space.
Okay.
Yeah.
So if I can get copies of these tests, and then I'll try to just give them to you Tuesday at math
Okay.
class, or if it would be easier, I can bring them to you
Okay.
next Wednesday night here, whatever is easier for you.
Okay, so you need test 1, because you threw it away or whatever. Here's test 2. I already have a copy of it. That's
How do we
one I
know
think
which one
we're,
is which?
huh?
How do I know which one is which? I guess it doesn't really matter.
Okay, just a minute. Let me just give you what I got, and then we'll go over what they are. That's, I need to make you a test 3. I need to make you a test 4. And here's a test 5.
Because people made pretty good on these tests generally.
Okay.
This was a 2-hour class, wasn't it?
Yeah.
Okay.
But I've been recording all this. I'm sorry.